Yes, so that was locality, again, mostly common sense stuff. Now the next one is the crash consistency. So key here is how to update the disk when crash happens. So the file system may crash if this happens, right? The electricity goes off, battery runs out, somebody cuts the wire, whatever. Lose power between any two writes. And thus the on this state may only partially get updated. Now, after the crash, the system would boot and mount the file system again. And given that crashes can happen anytime, how do we ensure the file system keeps the on-disk image in a reasonable state? It's a detailed example here. Now, let's first talk about a workload. So we're going to use an example. The workload is very simple. We have something, but we want to append a single data block to the existing file. Okay, we have a file. We just want to append something, right? Now, here we have an inode bitmap, 8 bits, and this is 1 per inode. We also have a data bitmap, also 8 bits. This is 1 per data block. And then we have inodes and data blocks. Now, inside of inode, we named it V1 because this is version 1. So here, owner is a Ramsey. Permissions, read-write. Size, there's only one. There's only one data. Okay, this is before the append. Now the pointer, 0, 1, 2, 3, 4, right? So the data blocks occupied is in index 4. So there's the pointer here. The rest of the pointer is null because we only have one data. Now, when we append the file, right? So we had D sub A, now we also have D sub B. Now the inode has to be updated. Now we termed it version 2. So owner permission is still the same. Now size updated to 2. Pointer 4, the next pointer 5, because we have appended. Now for this simple change, we had to make 3 separate writes to the disk, right? First, we have to update the inode. We also have to update the data bitmap and actual data itself. So it involved 3 writes. Now, recall that this write system call, it doesn't immediately just go right. It actually waits a little bit, right? And obviously, we're going to have some crash during this time. So crash scenarios. So we have, again, 3 writes. Now let's consider a case only one of those 3 writes made it through, right? Now there could be 3 different scenarios. One, let's say the data block is written, but not the updated inode or bitmap, right? So data blocks gets written, but there will be no inode that actually points to the data, right? There will also be no bitmap that says the block's allocated. So this is a problem. Second scenario, only the inode is written. Again, problem because inode now points to garbage data because data has not been written. We also have file system inconsistency because we now have a disagreement between the bitmap and the inode. Right? So the metadata are basically counter with each other. Similarly, let's say only bitmap is written. Same thing, we still have file system inconsistency because only one of bitmap and inode is written. And also now we have something called space leak because block 5 would never be used by the file system. Because bitmap says it's allocated, so we're not going to use it. So again, any scenario is still a problem. Since we have 3 writes, we should also consider cases where 2 writes are successful. So again, we have 3 cases. So let's say inode and bitmap are written to the disk. So the good news is metadata is now consistent. At least they agree with each other, except data is not written, so block 5 has garbage. Still no use. Second case, inode and data block. So again, one of only inode bitmap, so inconsistency. If it's bitmap and data block, again, no inconsistency. Now bitmap, data block, both are written, so there's no space leak, except there's no inode pointing to the file. So anyway, so it's the bottom line, no matter what, crash is a problem. So ideally, we want to have a file system from one consistent state. So let's say that's before the file got appended to another atomically, meaning after all the inode, bitmap, and new data block have written to the disk. Right? 3 writes, we want them all be done, ideally. Now, the issue here, however, is a disk only commits 1 write at a time. And crashes could happen anywhere in between. So we have something called a crash consistency problem, or some people call it consistent update problem, that results in, as we have already seen, file system inconsistency, space leaks, garbage data, etc. So let's study some solutions. The first is called the file system checker. How should we read this? Anyone? How did you read it? FSCK, okay, that's one. Some people call it FSCK. There are other people who call this. Everybody's on board with FSCK. Huh? Oh, that works. Yeah. The problem is somebody might not understand what that means, but or somebody might think you're actually swearing, but yeah. Some people call it FS check. Most people I know call it FSCK. Okay, you're supposed to laugh, but okay. Because it actually sucks. So this is like the basic way. So basically what it does is, okay, we're not going to try to do anything. If it happens, we'll detect and we'll try to fix a little bit. Okay. This will not resolve all the problems, but it will do what it can. So what it will do is it will go through all of these. First, it will check the super block. So it's basically do some sanity checks. So again, see if it makes sense. If there's anything corrupted, then you go find a different super block that looks okay. So you go see which ones are allocated, which ones are free. Then you go check the consistencies, right, between the inode and bitmaps, right? Because we saw when there are inconsistency, that's a problem. So you go check that, right? And you go do it from the root directory. You basically go scan the whole thing. Inode state, if inode has a lot of different information, you want to read all it to make sure everything looks okay. Checks the link count for each inode to see if it's consistent, right? So that's important. So it does that. Also check for duplicates. So if there are 2 different nodes referred to the same block, it's a problem. And kind of try to figure out which one's correct. If it is able to, then it will just basically, on point something that doesn't make sense. Back blocks, checks for back block pointers, then point to the location that lie outside of the file system partition. Obviously, something went really wrong here. So if it finds that, again, just undo it. Also does the directory checks. You want to make sure only the directory itself and the parent directory are the first entries, because otherwise something's wrong. And also that each inode referred to in a directory entry is allocated and no directory is linked to more than once in the entire hierarchy. So just go through one by one. Hey, if things happen, we'll try to fix it. So that's the attitude. So the reason is FSCK is because if you want to build a working FSCK, you need to have a very intricate knowledge of the entire file system. So it's very slow, right? From the root all the way down, scans, check. It will take a while. So it works, but it's very wasteful. So as disk and RAIDs grew, people start to look for other solution, right? I mean, if you look at the history of engineering, the first solution is far from perfect. But what's important is you actually are the first one to try to solve it, okay? So nobody loves it, but I'm sure whoever did this is very famous and everybody cited his or her document and all that. Anyways, so identifying a key problem, very important, not coming up with a perfect solution. Because there is no perfect solution anyways, but we have something better. Solution number 2, journaling. Anybody write journal or diary? Anybody? Or maybe a pictorial journal, maybe? No? Nobody wants to have a record of what happens in your life? How do you remember what happened when? Do you not need it? I'm sorry? Photo. Do you take a photo? And where do you store it? I mean, do you just take a photo on your phone and just put it there? Or do you like organize it somehow? Or do you like leave some kind of a caption saying what? And I mean, sometimes what? Print it out. To do what? And do you put it in your wall or what do you do? Put it in a drawer. So you print it out, so put it in a drawer that you're never going to open again in your life. Okay. Okay, thanks for sharing. Anyone else? Instagram. Okay. Or Kakao story? Instagram story. The story is the one, sorry, because I don't use it. So is that something where like it disappears within a day or something? So if I follow you, if I'm logged in for a day after you post a story, I can't see it, right? But you have record on that. Okay. I see. I see. What did you do before Instagram? Yeah. Oh, you did. Do you have it? So it's in a book. Do you keep it? Do you know where it is? Okay. Do you like go back and kind of read it once in a while? You should actually. No, the reason, and to be honest, I don't either, but we should, because it's self-reflection, right? You don't have to write it every day, but maybe when you have a major event, maybe you accomplish something, you're very successful, or you fail something, which is okay, right? Because we all fail. Why I fail? How am I gonna, return and succeed again? Whatever, right? But one of the inspiring talk that I heard, it was actually from, you guys know Professor Pesangmin of industrial engineering. So he said he has like shitload of books, all diary. And what he says is that once in a while, he goes and scans it, right? And these are like his past events. Now, we all live through our past and we become who we are based on all the past we lived through, right? But sometimes we forget, right? by looking at what he's written, let's say 7 years ago, it actually like, it reminds him of what happened, and then whatever happened 7 years ago versus all the things you learned 7 years somehow sparks into new idea. At least that's what he says. So all his famous stuff that like you can buy in our library, he says it all came in that way. Like, for instance, he's famous for what do call it, the pot, where if you don't water it, it actually goes sideways. Because when he was living in New York, he's like living by himself, so he's lonely, but he didn't want to have a dog or something. So he was, raising plants, but because he was lazy, he forgot to water it. And he wrote down in his diary. Then later on, he had some ideas about, what do you call it in English? Otugi. You guys know otugi, like that never falls? So he had some thoughts about otugi, and then those two combined. Basically, if I don't water it, and he used his engineering background to get it fall down, and that's how he came about. So he says all these companies, when they have this like full day workshops to come up with new ideas, he says that's bullshit. Like, nobody's gonna come up with new ideas stuck in a room. And he suggested instead everybody should write a diary or journal, because you forget what you did. You guys probably forgot the little tiny details that might happen that might have been really important to you, let's say when you're in junior high, by reading it, but with you reading it now, so journaling. But I think most importantly, self-reflection, because you guys don't have time to reflect. You guys have time to react, right? Oh, somebody posted a picture on Instagram, so I'm going to react. Oh, like. Oh, pretty. I want to go there too. Blah. But there's no reflection, right? Well, you guys respond to the KakaoTalk messages without thinking deeply, right? Because you have to write right away. That's react, not reflect. Right? So we need to reflect. Reflection. Okay. With that, so second solution is journaling. So there are two parts, write ahead and log. So some people call journaling write ahead logging. So when updating the disk, before overwriting the structure in place, you first write it down in a little note somewhere else on the disk in a well-known location so you know where it is, describing what you're about to do. Then we write it to a structure that we organize. So if a crash happens during the update of the structures you're updating, you go back, look at the note, and retry, because you know what you're going to do. Right? Obviously, the problem happens if the crash happened while I was journaling, and we'll talk about that. So by design, journaling adds a bit of work during updates to greatly reduce the amount of work required during recovery. So one might say, hey, how often does crash actually happen? But this is like, oh, I'm afraid crash is going to happen, so I'm going to write down all the stuff. But that's the design. If crash does happen, damage is huge. So I want to make sure I'm going to write a little note. Now, this is actually a very popular mechanism used in the database management system, and operating systems decided to borrow it. So basically, now we're going to have a field called journal. Within the journal, we have TXB, which is transaction begin. We also have TXE, which is transaction end. Both would include something called TID, so transaction ID. Now the middle three, and the familiar ones, inode, bitmap, and data, these are basically the contents of those three blocks. Okay, so some people just call that part physical logging. So again, there are markers that show beginning and the end. Okay, so that's journal. So now the protocol will work like this. Step one is journal write. So write the transaction, including transaction begin, all pending data and metadata updates, and the transaction end block to the log. And you wait for these writes to complete. Then the next step is checkpoint. So you write that pending metadata and data updates to their final locations in the file system. So you journal it first, then you go commit. Now, as I mentioned, problem gets trickier when we have a crash during writes to the journal. So here, what the system would do is it would issue a transactional write in 2 steps. First, it would write all the block except TXE. And you issue these writes all at once. And then it issues the write of the TXE. Now, the reason this is important is one of the good things about operating system is that disk guarantees that any 512 byte write will either happen or not. So there's no in between. If it's a 512 bytes, it's either written or it's not at all. Now, TXE ergo is 512 bytes. So if this went through, we're safe. So now we have an updated protocol. Step 1 and 3 are the same, but we now have something called journal commit. So actually, I forgot. So in the journal step 1, now it includes TXP metadata and data, no TXE. In journal commit, write the transactional commit block containing TXE to the log. Then you wait for the write to complete. And then we call this transaction is committed. Then you do a checkpoint. Now let's talk about how do we actually recover. All right, I mean, we only talked about protocol. We didn't actually talk about how it recovers. Now, if the crash happens before step 2, right? Crash happened here. Sorry. Yes. Just skip. Pending update, skip. Now, if crash happens after the transaction is written to the log, but before the checkpoint, so in between steps 2 and 3, the crash happened here, right? We do the redo logging. So scan the log, look at the transactions committed to the disk. Now these transactions are replayed and has to be in order. And with the file system, again, attempting to write out the blocks in the transactions to their final on this location. So this is basically the recovery part. If it happened before, then, just skip, it's lost. The last case, if crash happens during checkpointing, it's fine, it's okay. It's just not a problem. Now, next couple of slides are more of an optimization. Now, we don't want to have excessive write to the disk. Journaling buffers all updates into a global transaction. Now, the file system marks the in-memory inode bitmap, inodes of the files, directory data, and directory inode as dirty. And you want to add them to the list of blocks that form the current transaction. And when it's time to write these blocks to this, just making a single global transaction, so you don't have to go write a lot of times. So that's just, being smart. Just you batch all the updates. Now, sometimes your logs could be full or maybe very large. Now, this case, recovery would take longer because when crash happens, you have to go back far and read the whole thing. That's one problem. The second worst problem might be if it's full, there's no further transaction could be committed to the disk, right? And so the solution to that is something called a circular log or reuse the log. So here, once a transaction has been checkpointed, meaning, hey, it's done, then the file system frees the space it was occupied within the journal. So you want to mark the oldest and newest non-checkpoint transaction in the log in a journal superblock. Okay, so you're indicating which one should not be reused, but others, you can go use it. So again, optimization. So now with that, the updated protocol is you basically add number 4, free. Sometime later, mark the transactions free in the journal by updating the journal superblock. Sounds good, but we can't stop here because now compared to scanning the journal and replaying a few transactions, now basically, as opposed to scanning the entire disk like FSCK, now we just have to scan the journal and replay a few transactions. So now it's faster, but the normal operation file system is actually slower. Because for each write to disk, we are also writing to the journal. Right? So these are 2 writes. So how can we do better than that? So people thought, okay, because between writes to journal and writes to the main file system, there's a costly seek. So the new idea is something called metadata journaling or order journaling. Here, the actual user data is not written to the journal. Typical user data is the one that eats up the biggest chunk anyways, right? So in the journaling, no user data. Instead, you write the data blocks to disk first before the metadata is written to the disk. So further optimizing the protocol. Now update step 1, we do the data write first. Then we do a journal write, but we only do the metadata. And then journal commit. And we do a checkpoint, but we only have to checkpoint metadata because we're not journaling the data, and then free. So we're finally done. Now, one thing before we close. So if you look at the textbook, somebody had a quote saying, the tricky case happens when there's file delete. So the example that we use in the book is, let's say we have a directory called foo, and now directory foo is updated, right? So, and foo takes up the address 1000. Now let's say we delete the foo directory, all the files within an actual directory, poof, gone. And then we freed up block 1000. And then we create a foo bar, it's a file, reusing block 1000 for data. Okay, because now this space is free. Now, if you do metadata journaling, let's say a crash happened and we replay, right? There could be cases where we actually replay and update the directory foo, which would overwrite the foobar file. Right? So to solve this, solution 1 would be, let's not reuse blocks until the delete of the set block is checkpointed out of the journal. Okay, that's an idea. But I think we can be smarter than that. So there's something called revoke. So when you're deleting the directory, it will cause a revoke record to be written to the journal. So when you have that revoke, right? So when you're replaying, the revoked ones are never replayed. Okay, so the tricky case we mentioned would be handled in such a manner. Yes, the next two slides basically shows the journaling timeline, time starting from here and down. Yeah, it's just visualizing. The first case was when you're journaling data and metadata. The second case when you're only doing metadata. So as we mentioned, we first do the data, right? Then you have TXB. So basically you can issue TXB journal and data at the same time. Data must be complete first. Then you have a TXB and the metadata, and then TXE. When you're done, then you checkpoint and you're good. So that's the main crash recovery mechanism, the most important one, journaling. There are four variants, four different ones. It's a little more advanced. Just want to giving you a taste. I mean, if you're interested, you can go read. They have papers, but just a high level view. There's four of them. One's called soft updates. So this orders all writes to the file system to ensure that the on-disk structures are never left in an inconsistent state. So in order to do that, it requires knowledge of each file system data structure. So it's more like a brute force way to enforce it, but a lot of overhead. Second one is called copy on write. So this never overwrites files or directories in place. Instead, it places new updates to previously unused location on disk. And after a number of updates are completed, COW file systems flip the root structure of the file system to include pointers to newly updated structures. Third one is called back pointer based consistency. So there's no ordering in force. Instead, each data has a back pointer to the inode. So inode points to the data, data points to that pointer. You want them to be pointing at each other. If that's not consistent, then you know something's wrong. Optimistic crash consistency. Hey, why don't we just use checksum? That's the fourth idea. Yes, that's that. And you guys have a deadline on Wednesday, right? Ooh. Is it Wednesday? You guys know, is that Wednesday? No? Huh? Is it tomorrow? Tomorrow midnight? Okay. Yeah. Huh? Is it Tuesday midnight? Do you guys want Wednesday? Now let's make it Wednesday. Yes. And then next week, we're in February. I think that's the last lecture. I need to start thinking about finals. But yes. So one more lecture and we're done. Any question on today? Mm-hmm. So which slide was it again? Of the first part or the second part, or the combined part? Is it in the crash part? So it should be around 36. This one? Oh, we're talking crash scenarios? This one? Okay, yeah. Right. Metadata is consistent. They are consistent. They are consistent, not inconsistent. They are, because both of them, metadata I know got written, so they're in the same page. They're in tune. And if only one of them gets written and the other is not, now they're inconsistent. It's not, but the data is not written. So they have information about block 5, and the data is not actually that, right? It's garbage. So it's still a problem. So any scenario, we looked at 6 different scenarios, right? Everyone has a problem because we need all 3 written. Yes. Slide 7. This one? So how do we know how many block groups we have? Okay, how do we know the index of the groups? I mean, there's gonna be some information somewhere that we store all this, right? Yeah, it could be like a super block that shows where everything is. Yeah. Mhm. This? Okay. Right. So basically what this means is, so the first case is it could happen anywhere before 2 completes, right? So it could be in between 1 and 2, or it could be while in 2. Now, it means you just have to skip it because there's nothing we can do about this. All right? Yeah. Well, the thing is, first of all, like, because we haven't completed step 2. So once we complete 2, we know this is committed. We can reuse this and we can go back and replay. If this has not happened yet, meaning TXE is not in the log, then we know this is messed up. So we just skip. We don't do it. Yeah. So at least, so it won't recover, but it won't be inconsistent. Makes sense, right? So there's, I mean, we can't do everything. This is our best effort, but we know something's bad, but system is consistent. Maybe a user does something again, like when I lost my file, I just redo my file, right? But at least system's consistent. Was there somebody else here? 46. This one? Yeah. So you're talking, okay, keep going, yeah. Oh, this is per, so, okay, so, yeah. So the question is, do we have this per cylinder group? So super block. Yes, it's 4-cylinder group, yes. Now, the thing is, although conceptually, so there's a cylinder group, but in the actual system, the reason we had like block groups, because you have to kind of go with the address. So there's basically block groups, right? So for each block group, you're going to have the super block and all that. Was that the question? Is it okay? Yeah. 12. So basically what we want to do, because we had this rule where you want to put the similar one or related ones together, right? Right? Now here, let's say one file is super large. Yeah. I'm sorry, I lost you. Where? After some blocks are allocated in the first block group, the FS place the next large chunk of the file in another block group. The next chunk of the file is placed in yet another different block group and so on. Yeah. Right. So indirect. Oh, you mean basically. So I didn't understand. You couldn't find what? Indirect blocks. You mean the blocks that points to the next one, or? I mean, we didn't actually. This is a simplified conceptual diagram, right? So in the actual detailed implementation, there would be some field that actually, yeah, would do that. Anything else? Yes. 32. Right. Okay, so I think going into the implementation, if only TX2 is checkpointed, then how do we point to these, right? So, I mean, that's a data structure question. Yeah, I mean, there could be different ways to do it. Yeah. So if you want to make it neat, you kind of want them moved, but that involves read writes. So, I mean, different system might have different data structures to do this, but, that's not the details that, we're looking at here. Yeah. All right. We're done then. Thank you.